So welcome to this lecture. We finished with operations which are called pull back and push forward. So we studied this operation, introduced and studied this operation in general. They are operations on tensor fields. If you have mapping between two manifolds, then this push forward operation goes this way and pull back goes the opposite way, and it acts on tensor fields on these manifolds. Well, this operation has some problems. Sometimes it is necessary to define it pointwise, and sometimes it can sometimes means that if f is not injective and surjective, there can be some problems with this operation. For diffeomorphism that is injective and surjective operation, there is no problem, and this, by some miracle, acts always well, including the case of non-injectivity and non-surjectivity. So in this sense, pullback is better, but be careful to use these words. Both are very interesting mappings. And now I want to apply it to one very important case, which is induced metric tensor. But now it came to my mind that maybe I will also do one comment on the length of the vector before. Of a vector and length of a curve. We have two concepts of length. When we are at a manifold somewhere, we can have a vector here, and there is a concept GVV, which is the length of the vector, if G is positive definite, say. And there is a concept of length of the curve, remember? So these two objects are related, and it is useful also for practical thinking about vectors, that how they are related. It is very simple, that this vector along or according to one of the definitions is some gamma dot. Yes, each vector is gamma dot of some gamma. It means that there are curves here, one of them gamma, other are equivalent, and we can go along this gamma for some time, epsilon, and come here. So M is gamma 0, and there is gamma epsilon. There are 2 points. What is their distance? What is the length of this small path? By this, it is integral from 0 to epsilon dt g gamma dot, which is gamma dot, the length of the gamma dot in this sense. And what is integral from 0 to epsilon? It is epsilon times gamma dot, the first order. Yes? So now we see that let's call this some dl. What is this dl? It is the distance or the length, the distance between this point and this point. Yes? So this length of the curve, of this short curve. And so this dl is here, and it is the length of the short curve between gamma 0 and gamma epsilon along gamma. And what is the result? That it can be written like epsilon gamma dot. So it is a natural interpretation that this length is time times velocity. Velocity is the length over time, yes? So, but what is important or maybe surprising a little bit, that this concept of a vector is an element from T and M, so it is somehow point concept. It is bound to a point. So it is not clear what does it mean, a length of the vector which is sitting in the point, yes? But the vector is sitting in the point, but it is connected with some equivalence class of curves, and that's why it makes sense to relate two lengths, or yes, two lengths. One, the length of the vector which is sitting in the point, which is a point-wise object, with something which is not sitting in the point, the length of the curve. It makes no sense in one point. It is the distance between 2 points. Yes? So this is quite useful relation. For example, take E2, that means usual plane, and take vector this one, the basis vector with respect to polar coordinates. We have r phi, so the basis vector, this one. So this curve, which is in general here, is the coordinate curve of this vector, because it's coordinate basis. So for example here, where we have r and phi, it goes along phi with constant r. So it is, the curve goes like that, yes? This is our gamma. And what is this length? It is the length between, when phi goes to phi plus epsilon. So the length, this length here. Phi is big angle, epsilon small, infinitesimal angle. So what is this length? By this definition, it is epsilon times this vector, the length of this vector. What is the length of this vector? It is g phi square root. What is this? It is g phi element of the metric, which is r. So here it is epsilon r. Yes? And it is true by simple geometry. If this is r and this is angle epsilon, this length is epsilon r. And it can help a lot in some practical manipulations with differential geometry of the manifolds which you can see, like Euclidean manifolds or some surfaces in the manifolds, but we need the concept of induced metric tensor. But combining the concept of induced metric tensor on surfaces in, say, E3, with this idea can help a lot with practical finding of many things with this idea. Okay, so now I will go to the induced metric tensor. So sometimes happens, quite often, that we have a manifold without metric tensor a priori, but we have a mapping to a manifold which has metric tensor. And dimension of M is less than dimension of N. So if we have, and this F practically is, well, if it is an embedding. So embedding of smaller dimensional manifold to a higher dimensional manifold. So something like symbolically, this is M, and here is N, and here we have F. This is F of M, the image. So what can be done? This H is, of course, T02 tensor field, symmetric and non-degenerate. So we can apply the pullback operation to it. And we can introduce pullback of H and call it G. So here leaves H on the whole manifold N, and we pull back it here, so now we have M with G. Now what is clear? It is clear by the properties, general properties of pullback, that this is a tensor from T0 to M. Yes? Because pullback preserves the type of tensor. So if it was T02 on the right manifold, now it is T02 on the left manifold. It is easily checked that it is symmetric. Yes, so it is symmetric. And if the signature of this metric tensor is with only pluses, that it is a real Riemannian manifold, not pseudo-Riemannian manifold, then it can be shown that it is also non-degenerate. What is quite interesting that if this doesn't happen, it is not always true. It depends on the details of this embedding, which is quite important that in physics we have important manifolds with pluses and minuses in Minkowski space, say, or the curved space-time. And if you make pullback of the metric from Minkowski space to on some submanifold inside, it is not always non-degenerate. Although it starts from non-degenerate H, after pullback you can have degenerate G. So it cannot be used as a metric tensor because it is degenerate. Yes. So in this plus case it is safe. In the mixed case, it is not safe. You must check whether it is degenerate or not. It depends on how you embed your manifold to this bigger manifold. You have a very simple example on it as a footnote in the book. So have a look there. That what is this extremely simple example which shows you that it is like that. It is not a proof of this that it is safe for this case, but it is an example that in plus and minus case it can be bad. So at least in this case we have these three properties, that means that G is a metric tensor. Two. Yes, that not only H, but only this pullback. Now, we want to understand how it works. So what is the definition? Well, G on some two vectors is pullback of H evaluated on these two vectors, and it is, by definition of pullback, H F push forward V F push forward W. So what happens that if you have vector here somewhere your V and also W, but it is a problem to write it to one-dimensional line, but imagine that there are two vectors now, V and W here. If you push forward by F these two vectors, if here is some M, here should be some Fm, and your push forward vectors are here. They are in this image manifold. So they are vectors which can be treated either as that they are vectors in N, or in more details, they are vectors tangent to this image space. Not general vectors in N, but they are in N, but directed along this image manifold, Fm. So what is the idea? That we want to compute scalar product of two vectors sitting here. But here we have no instrument from doing it. We have no metric tensor, yes, before this pullback. So we push forward these vectors to the second manifold. There we have H. So we can put the push forwarded vectors to our H, and we obtain some scalar product of these two vectors. Yes? And we then claim that this is the scalar product of these two original vectors with respect to this G, by definition. So at the beginning we are without G, but we can use existence of H here and existence of F, which enables us to put our vectors here by this push forward and to compute the scalar product in this place in terms of this H, and then we define that this number will be the number of some effective scalar product sitting here. And so this is the idea. For example, imagine that we have E3, that means standard space XYZ, including the standard metric, because this is the difference between E3 and R3. So, H, dx, dx, dy, dy, plus dz, dz. And now we can have some formal sphere. What I mean that it is not sitting directly in this E3 as usual, but it is just an abstract manifold which is constructed from some atlas. A manifold is some set together with some coordinates and so on. It is not necessarily that it is here. Yes, it is a manifold S2 as without any embedding. Now we can embed it by some f, such f that it will become here. So what this f is in coordinates? Coordinates on the sphere are theta, phi, on some abstract sphere. Now the embedding is expression of x in terms of theta phi, y theta phi, and z theta phi. And we can compute the pullback. We will do it in more general, and after the computation, we obtain d theta plus sine squared theta d phi. You will see. It will be an example on exercise, simple. And by the way, if we want to have this, it should be such that it is a unit sphere. Yes. If it is sphere with some radius r, it should be some r squared here before. So this is the expression if the embedding is for unit sphere. And now, if we want to compute the scalar product of some two vectors, by this mapping, we formally, abstractly, we are not doing it because when we have already this metric tensor, we can put to this metric tensor any two vectors, yes, sitting on the sphere. So here, V, W. And what happens? They are mapped as three-dimensional vectors sitting in E3, which are tangent to the surface of the unit sphere, and compute their scalar product in terms of this metric tensor. It actually happens, but we compute it differently. We pull back metric tensor here, so we will have G here already, and then put it to the G. This is G. So G, V, W. Computations like that will be, well, in exercises, there are several computations, quite interesting. And what is written in each of these exercises that compute induced metric tensor from this embedding. It is some standard way how to do it, because we know rules how pullback is computed. So, for example, here, what does it mean? That if we have this F and this H, it is pullback of H. So with this F, compute the pullback of this H means that it is d of x as a function of theta phi cross y, because it is the beginning. Sorry. It is pullback of dx plus the other terms by the properties of pullback. It is pullback of dx, tensor product pullback of dx plus the same with other terms. Now, pullback commutes with d. There is an exercise. So it is d of pullback of x, d of pullback of x, plus with other terms. Now, what is a pullback of x? It is d of x composed with f formally. And what is this in practical terms? It is d of x expressed as function of theta and phi. Plus similar terms there. So what is that? For example, this function, in order to have this unit sphere, is what? It is sine theta cosine phi. Yes, here is sine theta, sine phi, and here is cosine theta. This is the real embedding of the sphere as a unit sphere in E3. So dx theta phi, according to this x theta phi, is d of sine theta cosine phi, which is cosine theta cosine phi d theta minus sine theta sine phi d phi. It is a gradient of this function. And then you multiply it by the same expression here, and put together, and you obtain this expression. Yes, you will see. This is one way how to do it, and for simple cases, the simplest one. But let's do it formally. For general case, if H is HAB y dy A dy B, so we have xi's here and y's here. So because it is a small dimension, there is bigger number of y's like x's, like here. Theta phi are 2 guys, x, y, z are 3 guys. So what is the pullback? It is pullback of all 3 guys, so it is HAB y expressed 3 x's, and now dy A as a function of x cross dy B as a function of x. And what is this? It is y over xi dxi. Here is b over xj dxj. So all together, and these are Jacobi matrices of this embedding. So it is altogether HAB yx, JAI x, JB J x, DXI DXJ. So here is GIJX, this induced metric, as their components or metrics. So the alternative way to compute it is to compute the components of this pullback. And what is here? It is Ij, it is J transposed G, J, Ij. This is matrix, or sorry, H. So this is some sandwiching of the matrix of the original metric tensor by Jacobi matrix from the right and transpose Jacobi matrix from the left. So if you prefer to compute Jacobi matrices of this embedding, you can also obtain the matrix first, the matrix of your metric tensor, the components matrix. It is this Ij, it is Gij, and then add the basis and you will obtain the complete expression. And by the way, this matrix is bigger than G, so it is some bigger square matrix, and in order that it could be multiplied, it is like that. Yes, and altogether you should obtain some smaller square matrix. So here it is H, J, J transposed, and this is matrix of your wanted metric tensor. So some examples, I will, well, this was the first example, more or less done here, not to the very end, but you can finish it and find that really it is like that. And by the way, the matrix here the matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. Yes, it is the matrix of components of this metric tensor H. So this is H matrix, and from here we see that matrix of components corresponding to this expression. Here is 1, here is sine square theta. So 1, 0, 0, sine square theta. So if you do it with the Jacobi matrices, you should sandwich unit matrix from here by some Jacobi matrix, and it's transposed, and you will obtain this matrix. So what are interesting examples mentioned in the book, and they will be in the offer for exercises. One of them is the standard sphere. It is, of course, very important to have metric tensor on standard sphere, this one. But there are also some other cases. For example, we can have a torus, which should be embedded somehow nicely in XYZ, yes, that some rounding around this z-axis. And there are introduced some nice coordinates there, some psi and phi. And you can do similar computation like for the sphere, that there is embedding to x, y, z here. You can read it from the picture, that imagine the picture of this torus, then find that what are interesting coordinates. The psi goes in this direction, and phi goes in this direction somehow. Maybe opposite this way. So you can find useful coordinates on your torus. Psi were in this direction, phi were when is this direction. Write down formulas for this picture, and then do either this computation or the computation with matrices, which you prefer, and find a metric tensor on torus, which I just read that the result will be A plus B sine psi squared d psi plus just B squared, phi here, and B squared d psi. What is AB? This AB, A is to the middle in this direction, and B is the radius of this. Here is B, radius of this circle. And A is also radius of the circle which is inside this torus, in the middle. So first of all, when you will have this exercise to be reported on the recitations, explain us the explicit formulas which correspond to this picture, and then explain us how to compute this result. Then there is a quite interesting problem, very, very simple from the technical point of view, that you can have a torus embedded to E4. The coordinates in E4 are x, y, z, w. And if you write this as cosine alpha, sine alpha, and cosine beta, sine beta, which is some parametrization of something two-dimensional embedded in E4, then you can compute, so this is our f. It is alpha beta going to x, y, z, w. Here are explicit formulas. Now, what is the topology of this result? Here is periodicity with respect to alpha. Here is periodicity with respect to beta. So if we put alpha beta plane here, here is some square, 2 pi times 2 pi. And here is the interesting part of the plane alpha beta, because all other alpha betas are already here by some periodicity. Yes? But there are some identifications that, for example, this point is the same point like this point, effectively, in this R4, yes? Because of periodicity with respect to alpha. This point is the same like this point because of the periodicity of beta. So usually it is drawn as a picture like that. And by this we mean that this side should be identified with this side. So the points are identical, effectively. Well, how can we visualize it? That we just put it together. Take a sheet of paper, just make this square, and glue together these two sides after some bending. And then after this, glue together these sides. And what you get is exactly torus, topologically. Yes? The torus is something which, when you go this, you come back into 2 pi angle, and you go in this direction, it is also periodic. So effectively, you have a torus sitting in R4 or E4. Yes? And now you can embed a metric tensor on this torus from these formulas. And if you compute it, it is very simple. You obtain d alpha plus d beta, which is a bit surprising, because if you compare it with this E3 or E2, this is E2 metric tensor, yes? And it is the same, just relabeling of letters. So it is exactly like in standard Euclidean plane. If you compute the length of this curve, the result will be exactly like in Euclidean plane. It is Euclidean result. It is called flat torus. So the only difference is that here you have this periodicity. So it is not a plane as a whole, but locally it has metric properties of a plane. It is a torus as a manifold, but with local properties which are like in the plane. So it is quite interesting object and used in physics. Now there is sphere S3. I will not give details here, but S3 embedded to E4. Some formulas, some result. Not extremely interesting for us, but you can compute it. Then what is quite interesting is a rotational surface. You have some curve rotated along S, and which gives you a so-called rotational surface. And it can be given either by formula Rz or Zr, where R, here is somewhere xy, and this R is R from the plane X. It is polar coordinate R phi, polar coordinate, and X in xy direction, yes? So here is R. Now, if you know some formula, either this or this, it depends on the description and also on the surface sometimes, you can compute metric tensor induced on this rotational surface in general. For example, if you put Zr equals R, yes, it will be a cone. So you can induce metric tensor on the cone. And then, if you will have a curve on the cone, you can compute length of this curve. Here is it. It is cone which has angle 45 degrees here. Yes. And also quite interesting thing is so-called pseudosphere, which comes from the equation that first of all we will have R3 with coordinates 0, 1, 2. It is something like Minkowski space, but not 1 plus 3, but 1 plus 2 Minkowski space. So our H, mu nu, is metric tensor with matrix 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. This is R3 together with this is something called E12. We already have had this, I think, in groups, that metric tensor of type 1 plus and 2 minuses. And now we can introduce the surface. Given by this constraint. This is a constraint in this three-dimensional space. So these constraints make something two-dimensional. And it is easily visualized. It is some hyperboloid, two-sheeted hyperboloid. If here is 0, and here is 1, 2, it is something like that. You can introduce useful coordinates there and compute metric tensor. What are useful coordinates? The difference of two positive numbers is positive number. So here it is useful to put cosine square alpha, cosine hyperbolic square alpha, and here this together, sine hyperbolic square alpha, and in order to get r squared multiplied by r squared. Because there is an identity this well-known identity, yes, similar to usual cosine plus sine is 1. For hyperbolic functions, it is cosine squared minus sine squared is 1. So using that, and it is in the relation that whenever you have some u squared minus v squared equal 1, you can put u is plus or minus cosine alpha and v is sine hyperbolic sine alpha. Yes? So it is the most general solution of this equation. Like with pluses, it is cosine and sine. And then there are two guys, positive. So first of them will be square root of that times cosine standard angle some phi, and this will be this times sine phi. Yes? It is an exercise in the book number 327, if you are interested. So you can have a look to details. And what is interesting on the result, I will write down the result. That result is minus r squared, and there is d alpha plus d alpha d alpha plus sine hyperbolic squared d phi d phi. When phi is this angle which I mentioned, this is cosine phi and this is sine phi. And what is interesting on this is this sign, that if you compute some square of some vector, some GVV, with respect to this metric, here is 1, here is positive number, here is positive number, here is minus. So GVV is negative. So you know the concept of positive definite bilinear form, and this is negative definite bilinear form. Yes, this metric and this metric tensor on this pseudospheres is negative definite. It is called space-like in relativity. Well, and now quite interesting object using induced metric tensor is the kinetic energy in Lagrangian theory. We already know what is important for understand this. It was, I think, last lecture, that the kinetic energy from the first year mechanics that this expression can be written like 1/2 something dot some matrix and the same thing dot. They are all coordinates. This is from R3n, because there are 3 coordinates in the R1 and 3 coordinates in Rn and so on. So altogether 3n coordinates. Also this is from R3n. So this is 3n cross 3n matrix, big matrix. And I remember that it is M1 unit 3 matrix. It is 3. And here Mn unit 3 by 3 matrix, and nothing outside the diagonal. Do you remember, hopefully, that something like that happens? So we learned that in the first year expression for kinetic energy of a system of particles, we can find a metric tensor which is more important than Euclidean metric tensor. Yes, because Euclidean metric tensor in this 3-dimensional space has no application in this business, but this tensor is important. It sits in the kinetic energy. Now, recall that we can make a picture that here is our R3n with this H. There is some tensor. This is 1/2 of H computed on gamma dot, gamma dot. What is gamma? Gamma is a curve which goes here, yes? Well, there is some gamma here. So it is given in coordinates as R1t, comma, and Rnt. So it is the curve given by the motion of the system of particles. And in a second year mechanics, I introduced the notation that call this RT without arrow, just bar. Yes, so it is now we have a different picture that we have something called configuration space with constraints already. So here is so-called good vector whose end ends in configuration space. It is 3-dimensional vector here, but such vector that it satisfies constraints. All points in R3n which satisfy constraints give you together some submanifold in your configuration space without constraints, and it is called M. It is called configuration manifold or configuration space. And it is a manifold because it is given by smooth constraints, and we learned in this course that by smooth constraints you typically obtain a manifold, submanifold of this big manifold. Yes, so now we can call it configuration manifold. And we introduced now on this manifold just some coordinates q's. Q1, Q small n. Small n is the dimension of this manifold. So now we can introduce a mapping, which was introduced also in Lagrangian part of our mechanics in second year. This important mapping. Maybe you remember, if you remember how we derived Lagrangian equations, this step was extremely important. It is a vital step in the derivation of this equation that we should have a parametrization of our vectors by some q's. Now we can look at this formula now, that here is our M, here is our R3n, and there is some F which gives us F of M as a subset of this R3n. And it is given exactly by those formulas, this F. So we can interpret these formulas as a mapping from something when you have coordinates q's to something when you have coordinates R1, Rn. And here we have H from kinetic energy. So here we have nothing on this configuration space, but we can add G equal FH, and then we will have a Riemannian manifold, also from this configuration space. This small one, not this original configuration space without constraints. Yes? So because we have a useful metric tensor in our big space, without constraints, and we can compute this on the big space, yes, even for R's which do not satisfy our constraints. Now we restrict just for R's which satisfy constraints. So we are working already only here. Yes. Whole life we spend here because there are constraints. So we forget about the rest of our manifold and we get this guy which is M with G. So it is a new Riemannian space. This is big Riemannian space and this is small Riemannian space sitting in the big one with induced metric. Now you can compute it. G, some AB as functions of Q's. It is F star of H, AB. You can compute it by official way how we learned to compute pullback now, yes? And this original H. And what you obtain is exactly the expression which we know from mechanics, 1 to n, this n, and here is R k with respect to QA dot R k with respect to QB. These R's are functions of Q's. And here is mk, they are weighted by mk. Perhaps you remember, maybe no, that this was called DAB in our course of Lagrangian mechanics in second year. Yes? And it was called the matrix of kinetic energy. It was an important concept. Now we see that this matrix of kinetic energy is nothing more as a matrix of induced metric tensor. And what about potential energy? Remember that Lagrangian was T minus U. What about U? We started with some U as function of this R. So U existing in all points of this original space. Now, we introduced U of Q's as this original U of R expressed in terms of Q's. This was our definition of what is potential energy in Lagrangian mechanics. Now, what is this? It is U combined with F. And what is this? It is pullback of U. So, here we need G. And this G is pullback of H. This U is pullback of original U. So we can conclude that originally on the big manifold we had H and U, two tensor fields which give us here this H gave us kinetic energy and this U is potential energy. This is 0,2 type tensor and this is 0,0 type tensor. So in order to define kinetic and potential energy in the first year mechanics, we actually need two tensor fields. One of them is metric tensor, 2, 0 and so on. And the other one is potential energy, which is 0,0 tensor that is a function. Now, in Lagrangian mechanics, we need also kinetic and potential energy, and we obtain them from this pair just by pullback of the mapping which is given by the constraints. Mapping of the abstract configuration space to the configuration space sitting in our bigger space. Yes? So here are G and u, and here are h and other u. Also 0,2 type tensor and 0,0 type tensor. So going to configuration space and doing a Lagrangian is take original Lagrangian from the first year, kinetic minus potential, and then change the kinetic energy metric tensor to its pullback and the potential energy to its pullback. And you obtain a Lagrangian on your configuration space already. Yes? So the idea of the pullback is very essential here, that the construction of the Lagrangian from the big space to the space with constraints is practically given by two pullbacks. Okay, what is the next? Okay, so this is all from this week when we studied mappings of tensors induced by mappings of manifolds, practically pullback and push forward. And now we can apply it in a very important concept, which is called Lie derivative. So I already start now the chapter 4 in the book about Lie derivative. It comes organically from those concepts of well, also metric tensor will be important there in some part, but in general, this pullback and also flow. It is a reminder that we introduced flow of W. Yes, it was already present. It is phi t corresponding to W. And how it works, this phi t, that here we have a vector field. We have a manifold with a vector field. And vector field gives you integral curves by this equation. They are solutions of these equations, or in coordinates xi dot is vix. So we first, if we have a vector field, we first solve the equations for integral curves. And if we have this is integral curve with this initial condition. Because they are first order ordinary differential equations, you need to say where we are at time 0. Now, if we are here at time 0, this will be beginning of our curve gamma, which is just solution. So we go along this V and obtain gamma t. And now we have a mapping. Gamma 0 goes to gamma t. For each gamma 0, for each possible beginning of this curve. So for any initial conditions. Well, there is a caveat. Sometimes it cannot be possible to find it for big T, only for small t. Then you speak of some local flows, but we are now interested. Well, local flow, by the way, is enough for definition of Lie derivative. So it is not restriction. If only local flow exists, still Lie derivative is there. Yes, but just for using of flows, it is sometimes unpleasant that you cannot use this for arbitrary big T. We had 2 examples on our recitations for it. But imagine that this is not problem. Now the important property of the flow is this one. Did I already mention this equation or not? Because I don't remember. I think that maybe not here. It is a new equation for you. Okay, so what does it mean? First, that it means that this is an equation of two mappings. Yes? So what performs the first mapping? That you are here in time 0. There is some, you are here in time t, and when you start at t and go the further s, it is, you go to t plus s. So first, the left-hand side is that you are here at t and you are here at t plus s. Yes? And the right-hand side is, well, maybe in the opposite way, that if you go in two steps, first s and then t, or first t and then s, you go to the same point. So these are the same mappings. Now, you can invert it, as I already told. Can you tell me the reason why we can invert it? Why it doesn't matter whether this order or this order is there? It is just from this equation. No other knowledge is necessary. Yes, because this is clearly reversible, that if you write here s plus t, it is the same, yes, because they are real numbers. So it is not possible to have this ts and not st, because otherwise it will be incompatible. So how we, first I try to explain what it says, then why it is true. It is some very simple using of properties of differential equations, that what is a flow, this is this mapping, and what is gamma, it is solution of this equation. So this property is somehow a property of solutions of those differential equations, and they are very easy properties, like uniqueness or something like that. Well, it is not important, but it will be important to understand it for a guy who will report it as an exercise in recitations. So it is simple exercise that why this happens. Simple, of course, if you use some strong theorems from theory of differential equations, but theorems which you know and which you used many times. So have a look to the hint. Yes, good idea. If you choose this exercise, the number of this exercise is 412. You will find a hint that which property of this differential equation you should use, and you should think that really, if I use this property, this is clear. Yes? So this is the meaning of the exercise, that by hint you know what idea you should think of. So now we see that we can go from V to its flow. And it is also possible backwards. If you know a flow, if you have some formulas, what are formulas of the flow? That xi goes to some xi t with initial condition, yes? That you should find for all x's the new x's. And it can be shown in some simple exercise that if you make differentiation of this equation in 0, you obtain the components of vector fields from which it came. Yes? So it is also a simple exercise, that how to go back from the flow. So if you have formulas for flow, you can compute components of vector fields easily by by mechanical thing, by some differentiation. If you have a vector field, you can find the flow. It may not be easy because you should solve some differential equations. Yes? So this way may be complicated, this way is trivial. Now there are some examples, but we already had some examples before. So, well, they are also useful, as many examples as possible. And now it is maybe useful to know that this flow is sometimes, and well, quite often, treated as a mapping like that. Our flow was mapping from M to M. Yes? This mapping is a mapping M to M. But it can be also written as phi without t, as M cross R. What are points by definition? This is Cartesian product. MT, pair, goes to phi tm in the original language. So instead of studying phi t, you can study this phi. It is a smooth map, so it also smoothly depends on this t. Yes. So it is just for information. I will practically not use this way how to look on flows, but it can be useful sometimes. So just an information. And now we can go to some, what is a Lie transport? Now we start from this. Yes, that whenever we have a vector field, we can construct its flow, and its flow is a mapping from M to M. This is the only important thing for the start. Now we can combine it with our knowledge. The second thing important, that where you have M to N, you can do F pullback, which gives you, which maps you tensors on N to tensors to M. Yes. And if F is a diffeomorphism, then you can pull back also vector fields and covector fields, anything. And if it is diffeomorphism, then F is okay for any type of tensor fields. Yes, because, well, sometimes you could have problems. Now, is phi t a diffeomorphism? Is it a bijection? Because of this property, which was here, t plus s is t s, we see that phi t minus 1 is phi minus t. If you compose phi minus t with phi t, you will obtain phi 0, but phi 0 is unit mapping. It is doing nothing. All points stand. So that means that it has an inverse. And it can be also proved, maybe it is quite hard, that it is a smooth mapping. Yes, this flow, smooth mapping, plus it has inverse, so it is a diffeomorphism. At least for those t for which it exists, small t maybe. So our phi t, at least for small t equal epsilon, can be used now as this mapping, and we can construct its pullbacks. Yes? So we can construct phi t pullback. Now, what mapping it is? It is mapping of tensor fields sitting on the right manifold to the tensor field sitting on the left manifold. Yes? But now the right and left is the same. So it is tensor fields on the right M to tensor fields to the left M, which is of course the same. So this is a mapping that you can map some A to phi t star A. How it works? It works by, as is pullback defined, that if you put arguments to it, you should push forward your arguments and compute it on push forward arguments, by definition of pullback. So here, if this is our flow, here is sitting our tensor phi t squared, phi t star A, say in this point, evaluate it. When we put arguments to it, we should push forward these arguments here. If here is some gamma 0 and here is gamma t, so we want to compute this tensor on arguments, yes, vectors and covectors. We should push forward these arguments to this point, because this is the phi t without star, this push forward. Sorry, phi t push forward, so the star is down. Yes, yes. But these arguments are here now. So in order to compute this complete tensor here, we should come here because our arguments are here, and we should insert this push forward arguments to A, which is sitting here. Yes. So the knowledge about this tensor is here is given from the knowledge about this tensor in a phi t of M. So it really pullbacks. But what does it mean, this pullback? Now, pullback is going from this point to this point. Yes, because it is pullback on this from M to M. So it is pullback on the same manifold, but of course not on the same point of the manifold, but the image point goes back to the original point. This is the pullback meaning now. That point-wise, it is this point to this point. But it is not mapping of points, it is mapping of tensors. So this pullback is mapping of tensor sitting here to tensor sitting here by going back against the flow. And now, if this is possible, we can think like something like that. That try to do this. What is it? That we can evaluate this at some point. What is this? It is A, which came from the neighboring point. Here is somewhere epsilon. So A was sitting here, and now it was pulled back. Now it is at point gamma 0, but at gamma 0 we have also original A. So now we have two tensors in one point. This came from gamma epsilon. This was originally at M. We can divide them or subtract them because it is a linear combination of tensors sitting at the same point. It is legal to do it, linear combination. And of course, multiplied by some number, 1 over epsilon, legal operation. So it is what? It is some tensor sitting at this point. And because it is doing on fields, it's true for any point. So in any point, you do something like that. In given point, pull back our A to the left, subtract it from the original A sitting there, divide by epsilon, and this is some new tensor field sitting there. And what it measures? It measures what is the difference between this and this, of course. So it measures something which resembles the idea of a differentiation. What is the derivative of a function? Yes, it is function in point x plus epsilon minus function x over epsilon going to 0. So we compare functions a little bit to the right with functions on the original point with the step epsilon. So this is exactly this idea, like here. It is some kind of differentiation, but now we are not differentiated function of one variable, but we are differentiated tensor field. Yes? By this idea that what is the difference of tensor field a little bit to the right with the tensor field just in this point with smaller and smaller step, the limit. And this is called Lie derivative of A in the direction of these gammas which were created from vector field V. So Lie derivative in the direction of vector field V, or yes, this is the definition. Yes, so it is very important definition that Lie derivative of arbitrary tensor field in the direction of vector field V, which gives the flow. Now imagine this flow is in Euclidean space the flow which produces rotation. We already computed some flows like that. Yes, for V equal minus y this plus x this, we found that this is the flow. What measure this Lie derivative? It brings you tensors from, say, here to here. Yes, this is t, it is t plus epsilon. So it measures how your tensor field reacts on rotations in this plane. That how it is changed if you do a rotation. So for example, if this will become 0 for some specific A, it is rotationally invariant. Yes? If it is not 0, it says that it is not rotationally invariant and it changes at some rate. And this is the rate of the change of this tensor field. So extremely important information about the tensor field, that how it reacts on rotations, when rotation is important. We had some other vector fields, say this guy produces translations. You can again compute this Lie derivative of some A, and it tells you how it reacts on translations. Whether if it is 0, it is translational invariant. If it is not 0, it is not translational invariant, but the rate of change is this Lie derivative. Yes? So we already see that many important mappings can be described as flows of some vector fields in physics and in mathematics. And that's why the rate of change of tensor fields with respect to the flows is a rate of change of these tensor fields with respect to something very interesting, like rotations, translations, I don't know, very wide range of interesting operations is given by various flows. So this answer in many situations is very important. And I want just to say that you can compute, for example, Lie derivative of metric tensor. Because metric tensor is a tensor, yes, and this is possible for any tensor field. In particular, this computation can be given by some formula which is usually mentioned in the general relativity books, and it uses something which is called covariant derivative. And there is no this formula, but only some other formula where is covariant derivative. It is possible, it can be proved that it is right formula, but it is not very good to understand Lie derivative of metric tensor in this way, because you don't very much understand what is it about. So it is much better to use this formula and to understand what you are doing. Yes? It is practical to use the second formula, that's why it is used, that it is practical, but in crash courses of differential geometry in general relativity, crash courses in some textbooks, it's quite a long time needed to explain properly what is Lie derivative. So they are often not doing it. But if you have not just crash course, but crash course plus epsilon, like here, it is much better to use official definition of Lie derivative and study its properties, because it doesn't need too much time, and it is really useful and worth the time, I think. So I just want to tell that there are also some other formulas in very specific cases, which are not so clear in their content, like this formula, that the content of this formula should be hopefully quite clear, and that's why the concept of Lie derivative in general is so important that it is, I think, important to tell it already in the first course of differential geometry, first semester. Because this is only introduced in the second semester for fourth-year students. This concept, I mean. So the Lie derivative in the second approach is only possible in the second year, but it is too late. Lie derivative is so important that we need to know about it sooner. Now, because we know properties of pullbacks, yes, or in general properties of any pullbacks, we studied, for example, how it behaves on tensor product. We know, yes? So from these properties of pullbacks, because this is based on pullback, we can now compute easily the properties of Lie derivatives. And when we compute enough properties of Lie derivative, it will be very simple to compute it explicitly in any case from the properties. So official definition, this is not so official. Official definition is d over dt at 0 phi t star a. Yes? This is practically the same like here. So, okay, so next time I will show you that what are the properties. For example, what is Lie derivative of A cross B? Yes. From this, it should be clear, because we know what pullback does on the tensor product, and also linear combination and so on many special cases. And then we will obtain a table that for tensor field of type Rs, you should give this term plus this term plus this term plus this term for each index some term and so on. There will be a table, practical table, how to do it for any particular tensor. So thank you.